Welcome to this session on business mathematics. My name is Ashish Jain. I'm an assistant professor at the Department of Computer Applications at the Bhopal School of Social Sciences. Our today's topic is logarithm. Let's begin with a brief outline of the course. I have divided this course in two modules. In the first module, we will be looking at basics of logarithm, the properties of logarithm, rules and laws of logarithm, how to find logarithm of a number, and some questions on logarithm. In the next module, we would be covering anti-logarithm, how to find antilog of a number, and numerical problems involving both logarithms as well as anti-logarithms. So let's begin our journey towards logarithm. The theory of logarithm is a tool that helps to solve complex mathematical problems by converting multiplication and division problems into addition and subtraction. You must agree with the fact that it is very easy to calculate addition and subtraction than to do multiplication and division. Now, take for example, you don't have any calculator to calculate. Now, in such condition, to solve complex problems involving multiplication and division, it is very tough. In olden days, when there were no calculators, mathematicians used to convert multiplication and division problems into addition and subtraction and then solve them using logarithms. The word logarithm is given by a Scottish mathematician, John Napier, from a Greek word logos, which means proportion, and athimos, which means numbers. Together they make as ratio number. Let us understand the concept of logarithm. Logarithms are a convenient way to express large numbers. For example, the base 10 logarithm of a number is roughly the number of digits in that number. For example, we have 1 lakh. It has 5 zeros. I can represent this whole number as 10 raised to power 5, where this number 10 is called base and 5 is called power. Hence, this power variable is our logarithm. We will understand this concept later. In the real life, a lot of things decay logarithmically. For example, hot objects cool down, cool objects warm up, things in motion experience friction and drag, and they gradually slow down. All these physical phenomena can be measured using the concept of logarithms. In computer systems, the number of steps required to solve a problem are logarithmic. For example, the time taken depends on the logarithm of the amount of data to be processed. Logarithms are closely related to exponential function. For example, if we have an equation y is equal to a raised to power x, then we can write this exponential equation in terms of logarithm as log of y base a is equal to x. We will see this notation later on. For example, radioactive decay, bacterial growth, population growth, compound interest, GDP, etc. All these phenomena are measured using logarithms. With regards to different bases, we have base 10, we have base 2, and we have base e. Base 10 is used by chemists in measurement of the pH value, which measures acidity of a liquid. Base 2, it is used in information theory and computers. It is used in transmission information and measuring the errors made and how to correct those errors. Base E is called exponential. It is used in calculus and it is probably the most commonly used base for calculation by mathematicians, where the value of E is equal to 2.718281828. Logarithms help put numbers on a human-friendly scale. For example, the power of 0, which can be represented as 10 raised to power 0, which is equal to 1, which represents a single item. The power of 1, that is 10 raised to power 1, is equal to 10, that is 10 items. So you see, just by adding this power 1, we have 10 times the value of a single variable. The power of 3 is 1000 items, power of 6, million items, power of 9, billion items, power of 12, trillion items, and so on. If we have power of 80, that is 10 raised to power 80, it is estimated that it is the total number of molecules in the universe. So you see, on a scale of 0 to 80, we have started from a single item and we have reached the total number of molecules in the universe. That's the power of logarithms. Logarithm provides order of magnitude. Magnitude means value. It means that a 10x difference is cooler than 1 digit larger. For example, in computers where everything is counted in terms of bits, that is zeros and ones. Each bit has a doubling effect, not 10x effect. So going from 8 to 16 bits is actually 8 orders of magnitude, that is 2 raised to power 8, which is equal to 256 times larger. This is used in measurement of computer memory in terms of bits, bytes, kilobytes, megabytes, gigabytes, and so on. There are many common scales that are used which use logarithms. For example, Google PageRank. Google gives every page on the web a score which is known as a PageRank, which is a rough measure of the authority or importance. So, a PageRank 2 site is 10 times more popular than a PageRank 1 site. Another example is Richter scale. It is used to measure the intensity of earthquakes. The largest human recorded earthquake is 9.5 on Richter scale, and it is estimated that the earthquake which caused the extinction of dinosaurs was 13.5 on the Richter scale. Another common scale is decibel scale, which measures the intensity of sound. All these use logarithms. In its simplest form, we can say that logarithm answers a question that how many of one number do we have to multiply to get another number? Example, how many 2's do we multiply to get 8? The answer is 2 into 2 into 2. That is, we get 8 by multiplying 2 3 times. So we had to multiply 3 of the 2's to get 8. It implies 2 raised to power 3 is equal to 8. Here this 3 is called logarithm. We will understand this later on. Now we come to definition of logarithms. Logarithm of a number to a given base is the index or power to which the base must be raised in order to produce the number, that is, make it equal to the given number. So if we have a raised to power x is equal to n, where x is power, we can say that x is the logarithm of n to the base a. It is denoted as log of n, and we put the a, that is the value of the base, in subscript. We call it as log of n to the base a is equal to x. Let us understand this concept further. So if we have a raised to power x is equal to n, we can write it as log of n to the base a is equal to x. Now here try to understand the answer of the first equation, which is the number n, is actually the input for the logarithm. So this n comes as a input of the logarithm. Now the base here is a. This a comes as a base for logarithm as well. So we put this a as a subscript, which is known as base. And the power x is actually the answer of the logarithm. So we write it as x. That means a raised to power x is equal to n can be represented as log of n to the base a is equal to x. Here x is called exponent, index or power, and a is called base. Now if you again look at the definition of logarithm, it says that logarithm of a number to a given base is the index or power to which base must be raised to produce the number. That is, if we raise this base a to the power of x, we will get the number n. Okay, let us take some examples. So we have 2 raised to power 3 is equal to 8. Here I can write it as log of 8 to the base 2 is equal to 3. Similarly, if we have 3 raised to power 5 is equal to 243, I can write it as log of 243 to the base 3 is equal to 5. Now there are 3 types of logarithms. First, logarithms with base 10 are called common logarithms or common log. We can write log of n to the base 10 as simply log of n. It is understood here that the base is 10. The second type of logarithm is logarithms with base e or exponential. They are called natural logarithms. It is written as log of n to the base e, and it is also written as ln bracket n. That means it is a natural log. The next type of log are all those logs in which base is neither 10 nor e. That is, logarithms with base a not equal to 10 or e are called special logarithms. We write it in the form as log of n to the base a, where the value of a can be any value except 10 or e. Now we come to properties of logarithms. The first property is logarithm of 1 to any base a is 0. That means log of 1 to the base a is equal to 0, as by the concept of logarithm we can write it as a raised to power 0 is equal to 1. Anything raised to power 0 is always 1. Hence, the value is 1. For example, we have log of 1 to the base 10 as 0. Similarly, log of 1 to base 25 is also 0. Hence, log of 1 to any base is equal to 0. The second property is logarithm of any positive number to base itself is 1. That means log of n to the base n is equal to 1. Why? Because n raised to power 1 is always n only. Take example, we have log of 10 to the base 10, the answer is 1. Log of 25 to the base 25, the answer is 1. So, if both the number for which we are finding the logarithm and the base are same, our answer is 1. The next property is logarithm of 0 to any base is minus infinite. Logarithm of 0 to base a is equal to minus infinite, as a raised to power minus infinite is equal to 0. The next property is logarithm of infinite to any base is infinite. Here the value of a is not equal to 0 or 1. We can write it as log infinite to the base infinite is equal to infinite. Here, in spite of having the base and the number same, our answer is not 1. It is infinite because our base is infinity, that is not measurable. Next property. If a is a positive real number and also x is real, then n is a positive number. We can write it as a raised to power x is equal to n, and here the value of n is a positive number. For example, we have 3 raised to power 2 which is equal to 9. Since the value of 3 is a positive value, so the value of 9 is also a positive value. Here, log 9 to the base 3 can be written as 2, which is positive. Next property. The logarithm of a number to base 0 or a negative base is not defined or not exist. It means that we cannot have base of any value to be 0 or a negative number. Next property. If a and b are positive real numbers not equal to 0, then b raised to power log of a to the base b is equal to a. Okay? Let us see some laws of indices that are useful in logarithms. Indices are nothing but index or powers. For example, if we have 2 raised to power 3 multiplied by 2 raised to power 2, since the bases 2 are same, we can add the powers, so we have the answer as 2 raised to power 3 plus 2, that is 5. If we have a raised to power m divided by a raised to power n, then if the value of m is more than n, I can write it as a raised to power m minus n, that is powers are subtracted. For example, 2 raised to power 5 divided by 2 raised to power 3, the answer is 2 raised to power 5 minus 3, that is 2 raised to power 2. Next, we have a raised to power m divided by a raised to power n. If the value of n is more than m, then we have 1 upon a raised to power n minus m. For example, 2 raised to power 3 divided by 2 raised to power 5, here this 5 is more than 3, so we can write it as 1 upon 2 raised to power 5 minus 3, that is 2. So it is 1 upon 2 raised to power 2, or I can also write it as 2 raised to power minus of 2. Next, a raised to power m upon a raised to power n. If the value of m and n both are same, it is equal to 1, because a raised to power m minus n, that is a raised to power 0, is equal to 1. For example, 2 raised to power 5 divided by 2 raised to power 5, the answer is 1. Next, a raised to power m whole raised to power n can be written as a raised to power m multiplied by n. For example, we have 2 raised to power 3 whole raised to power 2, the answer is 2 raised to power 3 into 2, that is 6. Next, ab whole raised to power m. It is equal to a raised to power m multiplied by b raised to power m. In this case, we have to open the brackets and to every value, we need to raise it to value m. So, for example, we have 2 into 3 whole raised to power 2, it is equal to 2 raised to power 2 multiplied by 3 raised to power 2. Next, a upon b whole raised to power m, it is equal to a raised to power m divided by b raised to power m. For example, we have 2 upon 3 whole raised to power 5, it is equal to 2 raised to power 5 divided by 3 raised to power 5. So, these formulas are used to solve logarithm problems. Now we see some rules or laws of logarithm. The first rule here is product rule. It says that logarithm of product of two numbers is equal to sum of logarithm of these numbers to the same base. A general structure of this law is log of m into n into something something up till p, whole base is a, it is equivalent to log of m to the base a plus log of n to the base a plus up till log of p to the base a. For example, we have log of 5 into 9 to the base 3. Applying this law, it becomes log of 5 to the base 3 plus log of 9 to the base 3. This law is important because it converts a multiplication problem into addition problem. The next law is quotient rule. Here, the logarithm of quotient of two numbers is equal to the difference of logarithm of numerator with the logarithm of denominator. The general structure is log of m upon n to the base a is equal to log of m to the base a minus log of n to the base a. For example, we have log of 34 upon 21 to the base 3. We can write it as log of 34 to the base 3 minus log of 21 to the base 3. Here, this division problem has been converted into a subtraction problem. The next rule is called power rule or power law. It says that logarithm of a number raised to power is equal to the product of index of the power and logarithm of a number to the same base. The general structure is log of m whole raised to power n to the base a is equal to n times log of m to the base a. Here this power comes out and multiplied with the log. For example, we have log of 5 raised to power 9 to the base 3, it is equal to 9 times log of 5 to the base 3. Next, we have change of powers law. It says that the logarithm of a numbers are given to the base a, then logarithm of those numbers can be obtained in terms of another base. We have three types of general formats for this. The first one is log of n to the base b can be written as log of n to the base a divided by log of b to the base a, and it is equal to n upon b. Another format, we have log of a to the base b multiplied by log of b to the base a. If it is used interchangeably, the answer is equivalent to 1. Next, we have log of m to the base a is equal to log of m to the base b multiplied by log of b to the base a. We will use these rules to reduce complex problems while solution. Okay. Now we come to the most important part of logarithm, that is how to find logarithm of a number. The logarithm of a number consists of two parts. The first part is called characteristic and the second part is called mantissa. The characteristic part is the integer part of a logarithm and the mantissa part is the decimal part. We will use some rules to find characteristics, and for mantissa we make use of log table. For example, log of 14 to the base 10 is equal to 1.1461. Here the integer part, that is 1, is called characteristic and the decimal part 0.1461 is called mantissa. Now, in order to find characteristics, we use certain rules and properties, and to find mantissa we make use of log table. Here one important point to be noted is that numbers having same significant digits and in same order have the same mantissa. We will use this property to solve certain questions. In this case, the characteristic value is decided according to the position of the decimal point. Now, properties of characteristics. First property, the numbers which are integral powers of 10 contains characteristic only. That means we can represent 10 raised to power 3 as 1000. So I can write it as log of 1000 to the base 10 as 3. Hence the characteristic value is 3. For 100 it is 2 since we have 2 zeros. For 10 it is 1 since we have 1 zero. And for 1 it is 0 since we have no zeros here. Okay. So for numbers that are integral powers of 10, the number of zeros in that number is the characteristic value. Next, the common logarithm of numbers between 1 and 10 lie between 0 and 1. For numbers between 10 to 100, the value of characteristic lie between 1 and 2. For numbers between 10 and 1000, the numbers of characteristic value lie between 2 and 3, and so on. Similarly, for numbers that are less than 1, suppose we have 0.1 and 1, the characteristic value lies between -1 and 0. For numbers between 0.01 and 0.1, the value lies between -2 and -1. If the value lies between 0.001 and 0.01, the characteristic lie between -3 and -2, and so on. Here, the value of characteristic can be negative. Logarithm of all numbers more than 1 are positive, and logarithms of all number less than 1 are negative. The negative characteristic like -1, -2, -3, etc. can be written as 1 bar, 2 bar, 3 bar. Bar is nothing but putting a dash over 1, 2 and 3, and similar with other numbers of negative type. Now we come to rules to find characteristic. The first rule is that if the number is more than 1. If the number is more than 1, its characteristic is equal to a positive integer, which is 1 less than the number of significant digits in the integer part of that number. Take a look at this table. Here, if we have a number as 1, so we have number of digits in the integer part also 1. Hence, the characteristic value is 1 minus 1, which is 0. For number 17, here we have 2 digits as integers, so the number of digits are 2. Hence, the characteristic is 1 less the number of integers, that is 2 minus 1, which is 1. In the next example, we have 3456.7. In this number, the integer digits are 4, that is 3456. Hence, the characteristic value is 1 less than this. That means 4 minus 1 is equal to 3. In the number 3.4567, we have only one integer digit, that is 3. That means 1 minus 1 is equal to 0 is its characteristic value. So I repeat, the characteristic of any value is the number of positive integers in it minus 1. Now, if the positive number is less than 1, that means it should begin with a decimal sign. The characteristic value is a negative integer which is 1 more than the number of zeros immediately after the decimal point with a bar sign. Let us see how. If you look at this table, we have 0.1 as the number. Here, the number of zeros immediately after decimal are 0. Since it doesn't have any integer value, so we cannot use the first property to find the characteristic, so we use this second property. Here, we have no zeros after decimal, so number of zeros are 0. We add 1 to this, it becomes 0 plus 1, that is 1, which is the characteristic value. But since this value is less than 1, so we consider this as a negative characteristic and we put a bar over our answer. Hence, the characteristic value is 1 bar. That means minus 1. The second example is 0.34567. Here, though we have many values, but immediately after decimal, we don't have any 0. So again, we have 0 plus 1, that is 1, with a bar as our characteristic. In the next example, it is 0.034007. Here we have 3 zeros, but we should always look for number of zeros immediately after decimal. So here, after decimal point, we have only one zero. That means 1 plus 1, we have 2 bar as the characteristic. In the next example, we have 0.00004. Here we have 4 zeros, we add 1 to it, it becomes 5, and we have to put a bar over it. Hence, the characteristic of this number is -5 or 5 bar. I hope you understand this. Let us understand logarithm table. So here, if you see, this is a logarithm table. This is just the first page. In logarithm table, in the extreme left hand column, we have figures ranging from 10 to 99, from top to bottom. And the topmost row contains the figures 0 to 9. Below each of these digits, we observe some numbers containing 4 digits or 4 figures. This part is called main body or the main part. There is also a side table on the extreme right, which is called mean difference. It contains 9 columns with heading 1 to 9. Also, the row values from 10 to 19 in the corresponding mean difference part contain 2 values of each position. If the third digit is more than fourth digit, then we will take the upper value, else we will take the lower value. Then we add both the values to obtain a total number, and we put decimal before the answer. Let us look back what we have covered in this first module. We have seen the concept of logarithm, we have seen the uses of logarithm, we have seen some properties of logarithms, rules of logarithm, and how to use a log table. In the next module, we would be covering how to find mantissa value and finally calculate the value of a logarithm of a number. And we will also look how to find anti-logarithm of a number. I hope this session is beneficial for you. Happy learning. Thank you.